So up to now, we have been going through several sections about determinant. So it is a good time to get a summary, to think about what we have done. And it is also a good practice for yourself to, after a few sections, and then try to think about why the instructor want to say this, and why the lesson want to say this, and what is the structure. Okay, so I would say there is a few big takeaway. Okay, so how to calculate the determinant? And basically, the simple answer is row operations. The easiest way, just like what we did last time, the easiest way is to use the row operations. And as a summary, you have several tools that you can do. The building block is that the identity matrix always have the determinant equal to 1. And whenever you do an operation, then the determinant will change correspondingly. Say, if you swap the row, okay, if you swap two rows, then the determinant will change the sign. Sorry, my writing is a bit small. Can you see from the back? Yes? Okay. Let me get it here a bit. Okay, so the first action, you swap two rows, then the determinant will change the sign. Here is a minus. Okay, and also, if you rescale a row, then the determinant will also be rescaled. So this is nothing new, it's basically the same definition. I just want to make a summary so that it's easier for you. Lastly, if you take one row and add its multiple to the other row, then the determinant does not change. So using all of these, supposedly you are able to calculate all the possible, all the matrices, calculate the determinant. Okay, so like what I say, this is the first, kind of the first definition that does not define the term explicitly， 就是说它不是很明确的直接定这个值。Sometimes the definition will just give you the formula, but this one it is asking you, okay, you know this, you know the identity. Next, you know the next one, you know more, you know the diagonal matrix, you know the invertible matrices. So it's a bit different, but try to get used to that. All right, then the second big takeaway is that the determinant, why we care about that? is because that we can consider its column parallelotope, the volume of that parallelotope, or use the row parallelotope. You can calculate its signed volume. And it is the same. You can just use the 3 rows to generate a parallelotope and calculate its signed volume, and it is exactly equal to the determinant. The reason is very simple, because each of them have the same definition. We run through 403, 404, and then 405. If you check out the definition in these 3 sections, then their definition is exactly the same. So basically they have the same quantity, although they have a bit different meaning. Determinant is a mathematical term without any meaning, but the column is using the column of the matrices to generate a parallelotope. And for the row, it is using the row. So it does not really obvious that it is always the same. Just give you an example to show what's the difference between the last 2. Say you have the matrix A, and we always use this one because somehow it is just easier. We got 2, 1, and 1, 3. And all of us know the determinant A is equal to 6 minus 1, which is 5. Oh, this is a bad idea. Sorry. Let me change one more. If you are writing too fast, sorry about that. Let's change the quantity a little bit. Sorry about that. I don't want the matrix to be symmetric. So let's try to change that correspondingly. 6 minus 2, it is equal to 4. Okay, now just by this matrix, and we are able to draw the picture by rows or by the columns. If you draw that by columns, then you got the vector, which is 2, 1. And you got another vector is 2, 3. So the parallelotope looks like this. On the other hand, if you draw this same thing by rows, you got the first row as 2, 2, which is here. And another vector is 1, 3. It is here. And obviously, these 2 things are not the same. They don't even have the same shape. The base and the height, they are different. But somehow, they can follow the same formula. You can use the determinant to calculate the area for these 2 parallelogram, and they have the same determinant, the same area, which is 4. So it is somehow surprising to see that column and row has the same area. So far, so good? It's not obvious, right? There are four vectors, and basically, it's very hard. You have 2, 1, oh, let me mark it. 2, 1, and 2, 3, and then 2, 2, and 1, 3. There's no easy transformation from here. It's not like you flip something, then you can get it. They don't even have the same shape. It's just something weird. But they have the same area. Okay, now lastly, we also have a section 402. And it is basically saying, if you are doing a lot of row operations, then you can find a lot of elementary matrices so that the product equal to the reduced echelon form. And make sure the first action should be the closest to A. And you apply several actions, then it becomes the matrix R. And if you wish, you can move all the things to the right-hand side using the inverse matrix or the reversed action, so that R is equal to F1, F2, up to Fk. Where Fi is equal to Ei inverse. So this is what you did last time for the group activity, and just make sure that you spend some time on this, because it's an important concept that every matrix you can do this kind of operation. Okay, any questions for this part? K 下课的时候，你做了 K 的动作，为什么这里刚刚做？哦 ，okay, this is important. So let me give you one example on here. So if you don't need to write it down, it's more important to just remember when you do the cancellation, you have to be aware of the order, okay? So say we have a quantity like equality like this, and what we can do is multiply by E2 inverse on both sides. Oh, on both sides, right? So you multiply the same thing on the left-hand side. 对 okay. I guess I make some mistake. Sorry. But let me finish this part. You multiply the same thing on the left-hand side. So the thing is that E2 will be closest to R because it will apply E2 first. So in the end, we got E1A is equal to E2 my inverse R. And then you can apply the same thing again. And this part becomes identity. It becomes A. So, sorry again, here is supposed to be F1, up to fk and multiply by r. But the big idea is that this k will be moved to the right hand side, and it is the first one to the right hand side. So it will be closest to r, and then you move k minus 1, move k minus 2, and then k, e1. I hope does this answer your question? Yeah. Okay, thank you.就是你可以留意一下它矩阵还是可以相消，但是消的时候要注意它的位置，因为它的顺序不能乱换。那谁先消要被放在最先执行的那边。所以突然有没有觉得建构式数学是有用的？也是两边一起消，你要两边一起除掉才可以做。你不能，就是你如果以前记除法会记说，就是换过去变除的，换过去变除，但是除的时候你要看是除左边除右边，然后还有谁先除的。Okay, but by the way, I'm sorry. I think the recording only take this part. And also the slide is only up to this part. Okay, now we formally get into 406. And we want to talk about invertible. Invertibility, the noun of invertible. Okay, so we recall that a matrix is invertible if its inverse exists. If you are able to find such a matrix A inverse, then it is called invertible. So there are several ways to think about this. If you are trying to solve A times X is equal to B, then X must be A inverse times B. Okay, is the solution, the unique solution. But this does not always happen because A is not always invertible. You have sometimes the A is so-called singular, and you have a lot of solutions, or it does not have a solution. And if A is invertible, then this quantity has the unique solution. And if you do some review of last semester, this behavior is called non-singular. In the previous semester, we talked about how to solve a set of linear equation. If the set of linear equation always has a solution and the solution exists, then this matrix A is called non-singular. So basically, non-singular is the same as invertible. We mentioned that before. And meanwhile, we also talk about something else. You can imagine that matrix A is sending a vector to A times X. Okay, so basically you have a vector sending x, send x to y, and so A inverse is doing the opposite work. You will send y back to x. Oh. Y will be sent back to A inverse times y, and which is equal to x. So this is like you have a set of all vectors that is Rn, and then you use a function called fa. We did that before. This function just means that you send all the x to the a times x. So it is again a vector in Rn. And basically, A is invertible is saying that this function fa is also invertible. It is a bijection. It is 1-to-1 and onto. So if A is invertible, then this function must be onto. I put it here, onto, which means that all the vector will occupy all vectors here after sending by the function. It will occupy all the space here. And on the other hand, the function is 1-to-1. Okay, so this function is very nice in order to make it invertible. So the following are equivalent. I just write it as TFAE, means that the following all things are all the same. If A is invertible, then we have several conditions. The range of FA, it is basically the column space of A, and it should occupy all the vector in the codomain. So this means that F is surjective. And on the other hand, we also have the kernel of A is equal to 0. And this means that this function f is injective. And the equivalent definition of this is saying that the rank is equal to n. And recall, rank is the number of pivots. After you doing all the row operations and get it into the reduced echelon form, you get n pivots. If this is the case, then the rank is equal to n, and A is invertible. And the opposite of the rank is the nullity. The nullity is the dimension of the kernel, and it is supposed to be equal to 0, equal to 0. So all these things are the same, and they all means that A is invertible. The last one that is our focus today, that is, if you want to know whether a matrix is invertible or not, then you can calculate its determinant. If its determinant is non-zero, then it is invertible, and vice versa. Okay, so try to come up with some idea that in, say, 2x2 matrix in your high school content. Is this true? Is that every matrix, if it is invertible, then determinant is not zero? Let's look at one example. Yeah, let me pause for a while if you are still writing. And sorry that the microphone does not work, but you can still hear me, right? You can either take a photo or just ask me to stop and or ask me some questions. But I think just this behavior, you have seen this before. In the high school, have you learned how to take the inverse of a 2x2 matrix? Yes? Okay, that's good, right? So if you want to, just I will write it down later, but when you are taking the inverse of a 2x2 matrix, you will do some action, but in the end, you will make the whole thing divided by the determinant. And if the determinant is zero, then you cannot do this work, right? So let's see. Let's see if we learned the same thing in the same way, or you can share me how you learned that. So we learned that the inverse, suppose A is equal to this, then A inverse is equal to, you add the minus sign to the off-diagonal entries, and then you swap the diagonal terms. But the big idea is that you will divide it by the determinant of A and apply this action to the whole matrix. And you notice that this quantity is at the bottom. It is the denominator, 在分母, right? So if it is zero, then this formula does not work. And if it is non-zero, then you can find the inverse. So as long as it is non-zero, then you are able to find the inverse. And that's another reason that we are talking about the determinant, why we want to study that. And in fact, for the higher dimensional matrices, we also have some formula like this, and it is called the aggregate. But I doubt that we have time to talk about that. Just want to let you know the same behavior also works for higher dimension. This formula is called aggregate. Just want to let you know. But as usual, when the dimension gets higher and higher, the formula is not so easy. So that's why we only tell you the second one. Okay, so this is the big takeaway for today's lesson, and let's try to give some justification to that. So before that, let's make an observation or an easy proposition, 性质, okay? If a matrix A has a zero row, which means that a row that is all zeros. Then the determinant of A is equal to 0. Right? Again, you can come up with some basic idea by yourself. 1, 2, 0, 0, and determinant of that is equal to 1, 0, and 2, 0. It is going to be 0. Right? Because it's not that important. I will just show you and then erase it. But now, because you are taking the math major, now you have to think about the definition of the determinant. If you go back to the definition tells you that we have 4 rules. But now you see these 4 rules, none of them is talking about this behavior. There's no rule says that if you have a 0 row, then the determinant is equal to 0. It says that determinant is equal to 1, and you can multiply by -1, multiply by k, and there's no way to do the 0. But it turns out that these 4 rules is enough to tell you this behavior. So let's give a proof of that. 开始之前我讲一下哦，就是你就是数学系里面会很在意这种定义的事情。那你既然定义没有讲的事情，就叫做是证明。OK， 刚刚那4条法则里面没有任何一条跟你讲说它的列是0，有一列是0，它的行列式子就要是0。所以呢，举凡没有出现的东西，你就是要说明一下。Okay, so we may suppose the first row of A, if you don't like the first row, just pick another one. Okay, without loss of generality, 不失一般性, you may assume that the first row of A is a 0 row. Okay, then you can do such an action. You can take the first row and then multiply by, say for example, multiply by 2. It looks stupid because it is a 0 row, so if you multiply the 0 row by 2, then A and B are the same. Basically, this does nothing, but the reason we do this is if we do this, then we can apply the rule that we learned previously. The rule we learned tells us that the determinant of B is going to be equal to 2 times determinant of A. But they are the same matrix, so determinant of B is also equal to determinant of A, right? Because they are just the same. So as a consequence, you have a quantity is equal to 2 times itself. And the only possibility is that the determinant of A is equal to 0. Question for here. So 我要强调的是说，既然都进到数学系了，要有一点坚持，就是说定义没讲的东西就是没有出现，那你不管怎样，你就是需要给一点说明。那你就只能用定义的那4条，你手上就只有这4个东西，你要完成这一件事情，所以才会这样好像在绕一条路一样。你没事搞一个 B 出来，但是呢，最后这个 B 又跟 A 一样，又没有什么好处。但是呢， 它的好处就是说，你一旦搞出了这件事以后，你就可以使用那一个 rule， 你就可以用那四条法则里面去做这件事情。Okay, so try to get used to that. If you feel like the logic or why we care about this, then you can talk to me. Okay, questions or can I move on? I guess the logic is not to, the argument is not long and it is not hard. The only thing bothers you is like what the heck you are doing. It's like why we want to care about this. But like what I say, all you have is the four rules in the definition. That's why you have to create something like this to apply the rule. Okay. Anyway, let me do a summary and to finish this lesson. I will give a brief reason for saying that A is invertible if and only if the determinant is not equal to 0. And whenever you are proving something like this, you say, okay, left-hand side and right-hand side is the same. Then you have to say, okay, if I have left-hand side, then I will imply the right-hand side. If I have right-hand side, then I will have the left-hand side. So starting with the left-hand side, again, Jason told us that you have to know what is the assumption. The assumption is that suppose A is invertible. And you have to go all the way. In the end, you say, okay, the determinant is non-zero. So because it is invertible, its reduced echelon form is the identity matrix. After a lot of row operations, the reduced echelon form is the identity matrix. Okay. And so we know A can be written as our assumption in the first slide. You will have F1, F2, up to Fk. Multiplied by the identity matrix. And that is to say, you can use the identity matrix, which has determinant 1, and you go all the way back to A, and sometimes you multiply by 1, you did not change anything. Sometimes you multiply by -1 if you swap the rows. Sometimes you might multiply by k if you rescale the rows. And all these things does not change the fact that the determinant is non-zero. So the determinant of A is equal to the determinant of F1 multiply all the things up to Fk, and all of them is non-zero. F1 to Fk, they are elementary matrices. And let me finish the last part. So now, if you want to prove the right-hand side to the left-hand side, you can start with the determinant A is non-zero, or you can use the contrapositive statement. Contrapositive means 否逆命题. Okay, so we say invertible imply non-zero. So the other case we can say if it is not invertible, then it is 0. And in the end, we want to say that the determinant is going to be 0. But this is much easier, and it basically follows the same philosophy. Suppose it is not invertible, then after lots of row operations, then it will becomes the it will becomes the reduced echelon form, and such that R has a 0 row. And again, A can be written as a lot of actions, reversed actions, applied to R. And this means determinant of A is basically starting with determinant of R and doing a lot of actions. But the nice thing is that now R has a 0 row, so this guy is equal to 0. So it's a product of a lot of things, and then the last one is 0. So determinant of A is equal to 0.